Hello, this is Ms. Nichols, and this lecture is on creating equations. The essential question is, how do scientists make an equation, and how can I check to make sure equations make sense? So when most ninth grade physics students think about equations, this is kind of what pops into your mind. This crazy sheet, genius people that have generated all these crazy things that all come together. And it's kind of like this magic universe that you think you could never possibly be that person because look how hard that is. Well, I'm here to tell you that equations get a bad rap. They're not hard to make, they're not hard to understand, they're not hard to use. You just have to understand the pieces of an equation and how they come together. And then all that gibberish all of a sudden makes a lot of sense to you guys. And so we're going to teach you how to do that because no one's ever taught you what the point of an equation was before. So that's what the goal of this lecture is. And before we go any further, I hope you are all asking, why are you making me do this? Because that's usually a question that teachers should be able to answer. Why do we have to create and understand equations? Well, the answer is because they save us so much time in our lives, and they make lives more efficient and much easier in the long run. So for example, if you wanted to know when you're going to get to grandma's house, it's an equation that's going to figure that out for you. Of course, our phones can do that now, but they're using equations. So somebody had to build the equations into the phone that let us do that. If you want to know how long your phone needs to charge, there's an equation that can describe that process of getting energy into the phone. Maybe you're a musician, you want to build a guitar that sounds good. You can use an equation to help you design and build that guitar. Or maybe you're trying to build a boat and you want to know how big to make that boat. There's an equation that can let you figure out the size of the boat to float and not sink when you're trying to use it. So equations come in everywhere. You can use them to solve all sorts of life problems in a much more efficient way than just building a lot of boats and seeing which one sinks, right? That's not the best way to go about that process. So in this class, speaking of building, we're going to be building our equations. We'll be building every equation together from scratch, just like the first scientists that used them. And one of the things I like to say is once you build it, then you own it. And that's true about equations too. Once you understand where the equation came from, it no longer is something scary or unknowable because you actually helped create it. But in case it reduces any of your anxiety, we will also always give you equations for your test. We have an equation sheet on the front. Most kids don't necessarily need that because you've built it, but it's always good to have a reference. Or, of course, you could always just build them again on the test if you needed to. You should also know that our goal in this class is to do more with less. We're only going to go through less than 10 equations over the entire year. And that's not because we're making this class easier. It's because you can do a lot with a few basic equations. They explain a lot of different things about the real world. And I want you to, part of the thing I want you to get out of this class is that a single relationship or equation can describe lots of different things in the world if you understand how it works. So there's really two steps to building an equation. Step number one is to identify the dependent variable that you are interested in learning about or understanding better, and all of the independent variables it depends on. So coming up with the dependent variable is usually the easy part because that's your research question, it's what you want to know. It is trickier to figure out all of the things it depends on. Sometimes there's some secret little hidden things, but at least in this class, we're going to keep it pretty straightforward. So let's say you want to make an equation to scientifically calculate the niceness of each of your teachers. This is useful because when you go into forecasting, you're going to use this variable to figure out which classes you should take this equation to calculate which teachers would be the best ones to take. So we're going to call this dependent variable n. And when you first think about it, you say, what do I care about in a teacher? Well, there's only two things I really care about in class. I'm going to decide that niceness depends on, number one, the amount of candy the teacher gives out, and number two, the amount of homework the teacher assigns. And those are the only two things that you think are going to be relevant when calculating n. So you've done the first step, you've identified the dependent variable and all of the independent variables that variable depends on. The next step is to figure out what kind of mathematical relationship the variables have with each other. Each of the independent variables with the dependent variable separate from each other. So sometimes the way we figure this out is by doing an experiment of some kind. If I wanted to know the relationship between distance and time. I could go out and measure distance and time, and that's what I could use for my my information. Other times you just sort of use your logic and reasoning, like when we're doing this one with the teacher niceness. Hopefully it's logical what kind of relationship we are intending to mean when it comes to those two variables. So for example, our first variable, which is how much candy the teacher gives out, if the teacher gives out a lot of candy, probably most of you agree that means we also have a lot of niceness. So lots of candy translates into lots of niceness. On the flip side, if a teacher does not give out very much candy or really bad candy like that Tootsie Roll, that's going to translate to a less nice teacher, okay? So hopefully when you see this, big making big and small making small, you're jumping to the correct mathematical relationship, which is when the amount of candy goes up, the niceness of the teacher goes up. That means there must be a linear relationship between C and N. Or when the candy goes down, the niceness goes down. That's also linear, right? It means that they trend in the same direction. We need to go through the same process for our second relationship, which is the amount of homework the teacher gives. Hopefully, many of you guys agree that the more homework the teacher is giving, that actually translates into a less nice teacher. On the flip side, if your teacher gives you not very much homework, most people assume that means that the teacher is very nice. So when you look at this situation, more making less and less making more, hopefully you come to the conclusion that the amount of homework going up, the niceness goes down. That means there must be an inverse relationship between this variable h, which is homework, and n, which is the niceness of the teacher. So those are the two relationships. We've got one linear and one inverse. The last step in building your equation is to actually combine the information that we've learned about our variables into the final equation. So what you do is you start by putting the dependent variable on one side of an equal sign. So I got the n, which is my dependent, all alone on one side of the equal sign. Then any independent variables that had linear relationships with n go on the top or the numerator of the other side. So we decided that candy was linear with n because more candy means more niceness. Therefore, we put the c on the top of that fraction. Any variables that had inverse relationships with n are going to go on the denominator, which is the bottom. So we've decided that homework, increasing homework actually decreases niceness, and that's why it goes on the bottom of this fraction when it comes to making our equation. Maybe later on, and that would be it, that would be our equation. But maybe later on, we decide that we underestimated the complexity of the teacher niceness equation, and there's actually some other variables that are relevant as well. So maybe teachers give out money, not this teacher, but some teachers, right? That would probably be another linear relationship. Maybe teachers give out stickers, and that would be another quality of a good teacher, and that's linear also. So those matter. And then maybe some teachers do a lot of yelling, and we're going to say, well, that's a bad thing, that's going to be inverse. So if you learn through your research or your logic that actually there were more variables, the way you put more variables into the relationship is you just multiply them together on the same side of the fraction wherever they belong. So if I wanted to put money, stickers, and yelling into this, I'm just going to make that bigger line. I'm going to multiply all my linear relationships on the top. So now it's candy times money times stickers. And on the bottom, I've got homework times yelling. So we got all our linear relationships on the top. We got all our inverse relationships on the bottom. And this would be our sort of new and improved equation for niceness that has a little bit more information than our original one. So why does this whole process of building an equation actually work? Is it just magic? Why does it work? Well, the word equation means equal, right? And it means that the two sides of the equation are always going to be equal to each other or balanced out. So if you do something to one variable in the world or in science, and it's in an equation, that means something on the other side of the equation is going to have to change as well in order to maintain this balance. If you increase the numerator of a fraction, if you make the top of a fraction bigger, so let's start with a fraction, 1/2. Let's make the top bigger, 2 halves, 3 halves, 4 halves, 5 halves, right? The bigger we make those numbers on the top, the bigger the value of the fraction. So if you increase variables that are linear relationships on the top of those fractions, they make the whole other side of the equation get bigger as well. Of course, on the flip side, if you make a bigger number on the bottom, okay, it's like we're dividing by a bigger number, that's going to make the whole value of the fraction smaller. So like we started with 1/2, now 1/3. That's less than a half. 1/4 is less. 1/5, 1/10, 1/1000th. That's a really, really tiny number. So the bigger that number on the bottom of the fraction gets, the smaller the value of the entire fraction, which is what's happening to the equation. So mathematically, that's why we build the equations the way we do, with linear relationships on the top and inverse relationships on the bottom. So scientists have known about this process for a long time, and mathematicians, and so they've created a bunch of equations. There's a lot of equations that are already out there in the world, right? And you've probably seen some of these equations before. The cool thing is, now that you understand where the equation came from, you can actually take an existing equation and figure out what does that mean about the variables and the relationships between them in the world, just based on understanding the way equations are put together. So for example, maybe you've seen this equation before, speed equals distance over time. We're going to be using that equation in this unit, but we can tell that distance is going to have a linear relationship with speed just from the equation because it's on the top of the fraction. And we know that time is going to have an inverse relationship because of where it is on the equation. Maybe you've used this equation in a math class or a science class before. Density is equal to mass over volume. Again, we see one linear relationship on the top and an inverse relationship on the bottom. This is a super famous equation that you've probably run into before. This tells me that E only has sort of these linear relationships. There's nothing on the bottom. E is related to mass and the speed of light squared. So we have these linear relationships that go to E. Both of those increasing either of those would make E get bigger. Nothing has an inverse relationship with E. So that's kind of interesting as well. This equation is a really famous one called the universal law of gravitation. It's the thing that explains why planets go around the sun and why the moon goes around planets and how satellites can be in orbit with each other. So it's a really important equation. And it looks kind of complicated, but you can see pretty clearly now that you understand equations that all it is two linear relationships. So the force of gravity equals, well, there's this funky thing in the front that's a G. That's actually not a relationship at all. That's just a number, like 4, 5, 12. It's a big number, but it's just a number. And then we have the masses on the top, and so M1 and M2, that's the mass of the two objects that we're interested in, like the Earth and the Sun. And those are both linear relationships with FG. And then on the bottom of the fraction, we have an inverse relationship with R, which is the radius or the distance between the two objects that we're interested in, and it's an inverse relationship with R squared. So that's a bit of a harder equation, but just understanding how equations are built allows you to understand where that equation came from and what does it tell me? It tells me that the bigger an object, the more gravity it's going to have, which probably you understood already intuitively, but also the further apart the objects are, so the bigger the radius, the smaller the gravity between them. So that's kind of an interesting thing that you can learn from that relationship. All right, that's it for this video. Please take a few minutes to revisit your essential question, which is, how do scientists make equations, and how can I check that an equation sort of makes sense through relationships? I've got a great comic that I love there for you to read as a little bit of a reward for getting through the video. Thanks for watching.